Hello everybody, Chris F.E. Jackson here. I found this video on YouTube from Julian Dancer, the same chap that puts up the ISS live feed. What this video is detailing, or some chap explaining, electric space propulsion, arc jets, ion engines and the EM drive, which is called the glorified microwave. So this video is going to be about 20 minutes long. I'm going to go through this, play it, and going to be talking about some of the aspects of the design of this stuff, just to give a complete, unbiased opinion of what I think it is they're trying to do. So, with that, I'll start playing the video on. I hope you can understand the guy talking. He does sound slightly Asian or American Asian, or maybe a bit of German thrown in, so yeah, so let's see what you got to say.
Hello everyone, today I am finally going to make an explanation video again. However, I am not quite yet continuing my Scramjet series yet. Instead, I wanted to take the kind of fitting time right now. I will reply to a request and kind of widen out that topic. So today I will finally explain to you how electric space propulsion works, or what different kinds of electric space propulsion systems there are, and how each of them works in response to a request to explain how arc.
Right, so here, a few plasma arc jet type electric space drive prototypes on display, IOS, whatever that is. Okay, so for those of you who may know, I did a video regarding the plasma contactor units, which are actually based on the Truss 1 of the ISS, and he will explain briefly what that is here. These plasma contactor units, which I discussed, actually had xenon gas, which was actually passed through a hollow cathode tube, and which was then ionized and blown out of the contactor unit as a plasma gas. This was to actually neutralize the static field around some of the arrays, and to measure the plasma density surrounding the station at that end were some Langmuir probes, and it was to totally neutralize any field build-up between the body and possibly the solar arrays, and would actually neutralize the environment for any EVA activity. So I'll just play this on a bit as he goes on to talk. Here we go. Right.
But can also be over-categorized. There are two categories that are actually practically useful right now. Then there is one category that is a bit more far-fetched. Actually, it's not really far-fetched, but its actual usefulness is still limited by its performance, and it's basically still an engineering challenge and will maybe become useful in the future. And one is a rather...
I want to stop it there. He shows this picture a few times. We know that this isn't obviously to scale. Okay. Now, what I want to look at here is what this is supposed to be, the Earth's magnetic field. Just bear that in mind. Now, if this is a magnetic field, yeah, you see these magnetic field rings coming here and there, other rings coming out here. Where are these returning? Is it how far out? I mean, that is not a true reflection of what the magnetic field would be for this type of object. I would have equal amounts, unless they're trying to pervade here that the sun is distorting the magnetic waves here. So I don't know. It just is. This picture is completely misrepresenting, even if it was a ball. It's completely misrepresenting it. Although I know it's not to scale. Ridiculous. It's another artist's impression.
The exotic space propulsion system,
NASA.
one of these more specific systems that only work under certain circumstances, like solar sailing, and is also not currently really in use for anything. Now I'll start with the first two, the first of which are electromagnetic or electrostatic engines, which basically contain the most well-known electric space drives, the currently also most used electric space drives, the ion engines, and they're basically all ion engines. There are, of course, some special types of ion engines. What they do is actually to use electromagnetic or electrostatic effects to accelerate ionic particles or ionized gas. The propellant here is any gas, usually one that is well suited for this, often xenon, and
Right, as he said, xenon. I may have said xenon, xenon, tomato, tomato, right? Okay, so here we are. So basically, uh, if anybody is old enough to remember the old TVs with the CRT, cathode ray tube, if you imagine this as a TV screen here, okay, and you had a cathode which was heated, so the cathode would emit electrons and would be accelerated through a vacuum tube and would hit a phosphorus screen in lines sweeping down and sweeping across, which would create the picture. And the beam was obviously magnetically controlled to sweep either side. So what they're saying here is basically a similar principle where you have a gas which is coming into here. It says electrons emitted by the cathode are collected by the anode. Well, okay, so a gas comes in here, okay, and the electrons are hitting the gas particles, which are actually ionizing them. Now I can believe that. Yes, that does happen. That can happen. So with these magnets here, they call them the ring magnets that create and enhances ionization. Well, I can't see how that would enhance the ionization. I think it would focus it more because the magnetic field contained within this, the electron and the ionized xenon particle, would be net negatively charged. So the field here, I can't see how that's creating more ions. It's just the density of the gas that's coming in and the electrons hitting them to ionize it. So, but as they say here, electrons hit atoms to create the ions. So we have a positive grid. So, negative to the positive. And then they have this negative grid here. So I'm really not sure why they would have a negative grid, because that would repel the ions that are negatively charged. And then they say here an ion beam. An ion beam. So they're saying that this is creating the thrust. Neutralizing cathode. I have no idea if that's a probe that's going in. I'm not sure why you would need that. Ions electrostatically accelerated between the grids. Positive grid, negative grid. Right, so I have a question about that. I don't understand why they would have a negative grid there for a negative ion to electrostatically increase the acceleration. Unless they're actually forced through, and by the time it gets to the negative grid, it's repelling them. So that would be pretty handy, wouldn't it? So let's move on.
this gas is ionized, so the atoms of this gas are charged, and then they can be accelerated.
Is it me, or does that look like a speaker? Who knows?
By electrostatic effect with two electrodes, or more or fewer, depending on what specific type of design you make. You can add magnets or electromagnetic spools to guide them or to guide them in circles to gain more cycles of acceleration and increase your specific impulse. But the basics is always that you use an electrostatic effect, an electric field, to accelerate charged particles, which are then your exhaust, your propellant. They propel your spacecraft in the opposite direction according to Newton's third law as you accelerate them backwards. They can reach extremely high specific impulses, so they can be extremely propellant efficient, but actually all these electric engines are energetically really efficient, but that still means they're limited by the conservation of energy plus a little thermal loss. So high specific impulse means that you need a lot of energy per thrust, as you have to apply the force that is your thrust over a higher velocity.
Okay, so as you said there, you need to expel a high lot of energy to create the thrust. He's calling it thrust. It's an ion beam. Okay, now again going back to the old CRT, the old cathode ray tube, to get that stream of electrons to be accelerated through the vacuum towards the phosphor screen, you had a net positive charge on the screen in the form of 14 kilovolts. That's 14,000 volts of DC voltage. Low current, so it technically is an electrostatic field, if you like. Now, to generate that 14,000 kilovolts, you had a step-up transformer, which is quite weighty. All right, so I don't really know what in terms of the size of this. It doesn't look that big. Some of the other ion beams look slightly larger, but to accelerate the gas over a short distance, I would expect to have a similar, if not greater, static voltage of 14 to 20 kilovolts. And again, the weight required for that has to be a negative effect regarding the thrust you would need. Now, he talks in terms of thrust. He mentions something here, which I'll stop it later on, which is very poignant. I'll play this on a bit.
Now, of course, the specific impulse of ion engines can be throttled. Essentially, it's not really the engine throttle, but you can reduce the specific impulse of a ion engine by design, or in some models of ion engine also during the flight.
You could always turn the gas down,
which does give you a better thrust to power consumption ratio in exchange for a worse thrust to fuel consumption ratio or propellant consumption ratio, but it does make the engine unoptimal, as the thrust weight ratio in ion engines is usually not that great, and if you reduce the specific impulse of an ion engine to be around that of a normal rocket engine, you'll obviously come out at a much worse thrust weight ratio. So it might be better to use a different type of engine if you don't really want an extremely high specific impulse. These actually range up to 6,000 seconds easily. The second type of electric space propulsion system is the thermal-electric engine, which actually is by definition an electric rocket engine, and is also what was originally asked for. Now these perform somewhere pretty much in between the ion engine and the ordinary rocket engine, and they also work a bit like a ordinary rocket engine.
Okay, so they work like an ordinary rocket engine, somewhere between an ion engine and a jet engine. Now, look at the size of this thing. These could be what? M8, M10 bolts, this small thing here. Now, if this is supposed to be in interstellar space or in a vacuum, how on earth are they going to get rid of this heat? That's the first thing, and this looks quite small. So on a larger scale, imagine the energy you would need. Would these be the main thrusters for an interstellar rocket? Who knows? Let them carry on.
Although their performance is a bit closer to the ion engine. What they do is actually to heat up some sort of propellant using an electric effect or an electric heating system.
Okay, so he's saying they're heating up the propellant through this. Now this is a DC arc jet, they're calling it. So I have an anode, which is tungsten, and I have a cathode, which is thoriated tungsten. Now, thoriated tungsten, if I can explain, thoriated tungsten is a special type of tungsten which is used in these welders. Yeah, these MIG or TIG welders, one of them, to create your spark when you get your weld, and high localized heat for melting metal, and so they're using a gas. I'm trying to work out what gas they do use for these welders. Anyway, so they're talking about heating the fuel up, and then it just seems to burn through here, and you're constricting it, and out it goes. There's your thrust, people. Looks just like a welder, really. Let's carry on.
And then expand it to through a nozzle,
Yeah.
just like any normal rocket engine, and then propel it and gain thrust.
Just like a normal rocket engine, to propel it with thrust. Look at the size of this thing. It is minuscule, yeah? And it's glowing red hot, white hot there nearly, and that's showing, pervading as if it's thrust. Now remember, to get thrust, you have to be hitting something. The propellant has to be propelling against something, no matter what it's made of. Okay? Let's carry on a bit.
Through the expansion through a nozzle, just like a rocket engine, just except heating it up by chemical reaction in a combustion chamber. It instead heats the propellant up by an electric effect on electric heater, which can reach high temperatures while using pure hydrogen or pure helium as a possible propellant, and thus can reach really high specific impulses of up to 1500 seconds or even 2000 seconds. Of course, these can be theoretically combined with
Okay.
normal rocket engine. You could have electric heating plus a chemical reaction, but that would drastically reduce the actual advantage of a electrothermal engine, because the big advantage is that you can heat up your propellant, but the propellant can be a really light element like hydrogen, which then gives you a really high specific impulse for your temperature. And to reach such a high specific impulse with a fuel mixture that actually contains an oxidizer and actually burns as well would mean that you would also have to reach really high temperatures. So theoretically, combining a electric heating with a chemical rocket engine could give you a better specific impulse than a normal rocket engine.
Okay, so the thrust of this, and combine it with a rocket fuel chemical engine, I would think it would be like adding a candle to a blast furnace.
But practically, in order to reach a significantly higher specific impulse than a normal rocket engine, you need incredibly hot combustion chambers and nozzles, and that is just simply not quite practical yet. Then, of course, there are different types of electric heating engines. There are the actual arc jets, which are relatively popular. They're mainly developed at ERS, which is the Institute for Spaceflight System, the German acronym meaning Institut für Raumfahrtsysteme at University Stuttgart, where I actually study. And there are several test models bound to fly within the next time on a small communication satellite and on a lunar probe. And arc jets heat their propellant by using an electric arc. They have two electrodes, usually one of the electrode being the inside of the nozzle itself, which of course then has to be limited to the beginning of the nozzle. You don't really want to extend that electrode all the way to the edge of the nozzle, which is, there are several techniques how you can do that. Usually there's a gas film used to do that, and the other nozzle is essentially a rod inside the fuel injection or inside the nozzle, and between these electrodes you have an electric arc, basically like lightning, and you use that to heat up the fuel.
Hang on. You have an arc of lightning which you use to heat the fuel up. So, lightning or discharge would be a voltage. Now, to convert a discharge into heat, I would need some sort of resistance to generate current. It's the current and the power which would create the heat in the propellant, not the voltage. So I think he's either misquoting something or he's completely wrong.
Which is not only quite powerful for its weight, but also really efficient, since the electric arc mostly heats up the fuel actually, because it's the arc itself only is in the fuel itself. The arc is basically a property of the fuel, so the fuel essentially heats itself, and most of the resistance is in the arc, so most of the power gets lost in the arc. So most of the heating actually hits right in the fuel or in the propellant. And there is a different main type of thermoelectric engine, which is the resistor heated engine, which actually uses some type of resistor, essentially
Some type of resistor?
a block of material that has a relatively high but not too high electric resistance.
Please tell me, can anyone tell me what a value of not really high but not too low a resistance is?
And you push electricity through it and it gets hot.
You push electricity through it and it gets hot. Now that's really scientific, isn't it? I would have to have a potential difference to push current through a resistor, a force.
And then you can hold that hot resistor into the propellant and thus heat the propellant up, which is less efficient but simpler to design in some ways. And of course there are theoretically other ways to heat up propellant electrically.
How about a spark plug?
Now the third main type of electric space propulsion system is bit more exotic, but actually really simple. It's basically a light bulb or a radio dish. You can actually directly use light as your propellant. Now
Now listen very carefully. You can use light as a propellant. Now listen to what he says about light, theory of relativity, or what he perceives of it. Listen to this.
can spark discussions in Facebook comments between people who think they know physics, but it is actually long proven that light has an impulse that's in our standard model of physics. Light does not have mass, yet it does have an impulse, and people will bring up the equation for impulse, which is mass times velocity, but that equation is only in Newtonian mechanics and not in actual relativity. So for speeds approaching the speed of light, that equation is no longer exactly true.
It is true or it isn't. Not exactly isn't very scientific now, is it?
And at the speed of light, you actually can't have anything with mass at the speed of light, but at the speed of light something can actually have impulse but not mass.
According to the theory of relativity.
It actually has impulse according to its energy converted to mass by the equation of relativity. it sounds complicated, but what it basically means is that light doesn't have mass, but it has energy and it has impulse, and its impulse is essentially its energy divided by the speed of light.
Which must be infinitesimally small. Really small. Otherwise, this dish would fall over.
Which is rather small since the speed of light is huge, so anything divided by the speed of light ends up being rather tiny. But yes, it does actually mean that anything giving off light or any electromagnetic radiation does actually have a certain knockback according to Newton's third law, which does actually still hold true in relativity.
Okay, now he's mentioned Newton's third law. Let's bring it up, shall we? Right. Here's a quick one. Newton's third law is, for every action, there is an equal and opposite reaction. This statement means that in every interaction, there is a pair of forces acting on the two interacting objects. The size of the forces on the first object equals the size of the force on the second object. So, when we have a man here trying to pull against an elephant or a wall, the wall is stationary, he's pulling, so the wall is pulling back. So, if I emit light from something, or an ionized beam from something, it's escaping. So it would have to have mass, eject a certain amount of mass before this would actually going to be trying to resist against it. It has to have mass, not impulse.
Of course, many light sources give off light in several directions and so on, but you can use mirrors, or you can use a radio dish or a specially designed antenna, and you can direct electromagnetic radiation or light or microwaves or radio waves or gamma rays or infrared radiation or ultraviolet radiation, whatever you like, into one direction and get a Newtonian recoil and gain thrust through this. Of course, it does have a very low power consumption, thrust to power consumption ratio, a very high power consumption to thrust ratio, as that ratio is the speed of light. That is still assuming a very efficient light source, but most light sources are actually very energy efficient.
Assuming, yes, of course, assuming a very efficient light source. What's the most efficient light source we know? Well, the sun, perhaps.
Which does limit your thrust weight ratio already, because you need a heavy power source, and then the thrust weight ratio of the light source itself is usually not that great. So yes, that does kind of demystify the EM drive. The EM drive is basically a glorified microwave. The reason that it is said to be or appears to be physically impossible is not because it doesn't use any propellant or any propellant with mass. The reason that it seems physically impossible is
So the previous drives did have mass? Ionized beam have mass, yeah? Is that what you just mean?
because there seem to be no radio waves escaping it or no microwaves escaping it, but there are, and that is actually getting really complicated. The microwaves basically escape it without being measured as escaping it, and that's where it gets really complicated and not quite yet understood. But the idea of fuel-less propulsion is not physically impossible and not new, and the EM drive isn't very good at it either. It has a worse power consumption to thrust ratio than basically any radio dish. But it is quite interesting because it's not yet quite understood, so we might learn something new about physics from studying it, and that might then help us design better space propulsion systems. But that's still far off in the future. Then the fourth type of electric space propulsion is a bit more exotic. It's actually as it doesn't really give you a thruster that you could put on a spacecraft and you turn it on and it produces thrust in its opposite direction, and you can have several thrusters and maneuver your spacecraft and apply thrust, but rather it uses outside circumstances. That's the magnetic field based propulsion, where what you essentially do is you use electromagnetic effects to propel yourself against an outside magnetic field. So it actually is comparable in some ways to a solar sail. It does use outside circumstances. You can use any magnetic field, like the magnetic field of Earth or the magnetic field of any other celestial body.
So any magnetic field of any celestial body. Let's hope when you move away from one celestial body, you'd be able to reach another celestial body's magnetic field, sorry, and then perhaps you could reconfigure your magnets to actually cause your vehicle to attract to it. Complete nonsense. Complete nonsense. How would you start to embark on that? How would you measure the magnetic field of celestial bodies?
Magnetic field supplied by a space station with an electromagnet.
Oh, I see.
Depending on what you need for your specific concept, but the idea is to use that magnetic field to move a spacecraft, which I am not going to explain in full detail, but there
That's
are
a
several
shame.
ways, of course, you can do that, and depending on what type of electromagnet you have on board and how you use it, you can then, for example, pull yourself towards another magnetic field source or away from the source of the magnetic field, or actually perpendicular to it, depending on what kind of equipment you have and what kind of concept you're actually making, but they're not really in any practical use anywhere in the near future. So this was
Nor
a
will
brief
they be.
overlook of the types of electric space propulsion systems there are. I hope this was kind of interesting for you. I'm always open to requests or questions, and as always, thanks for watching.
Thank you. Well, there you have it. I must admit the models previously looked they were quite small. I don't deny their existence, but how they could actually propel tons
Test models
and tons of equipment, even if you scale this up, the amount of energy needed to actually produce this, to overcome the weight of this for propelling within a vacuum. That's what they're talking about, really, aren't they? As opposed to chemical rocket engines producing thrust. Yeah, okay. Yeah, I really don't care, but it's as a demonstration. Yeah, I could believe it if you use that in the atmosphere. It doesn't look that efficient to me. But who am I to say? I'm not an expert. I'm just questioning it, and the way it was presented was probably shocking, I suppose. I don't know who this chap is. It doesn't actually say anything in the chat. It just says sorry, in the description here. It says nothing at all. So that's that. All right, people. So there we are. There's more propulsion rubbish, really. Some people like this sort of stuff. It is interesting to a certain extent of what you can do, but regarding it to be able to propel future craft, nah. Okay, thanks for watching.